talk about TBA.
Oh, yeah. So that's the title, Braids, Cosimplicial Identities, Spreadability, Subfactors. So I will take you to a short journey connecting these things. And that's essentially the work Klaus referred to as the joint work with
Okay. Yeah. So that's joined with Gillian Evans and Klaus Koestler. And it's on the archive, so I can. What I wanted to do is to explain some of these things in some detail. A lot of it is actually rather elementary, so I can explain how it works. So Klaus used that to start these analogies with the Thomson group. The original idea was to understand better in a categorical way our earlier ideas to use braid group representations to get distributional symmetries. And interestingly, we found some connections to homological algebra, namely to these cosimplicial identities. So, and then of course, the whole scheme can then be applied in particular to subfactors, because you have braid group representations in that case. So this is just an example which gives some light here on subfactors from a different angle, which may be interesting for some questions. So everybody knows what braids are. So the Cosimplicial identities, you've already seen that in Klaus' talk, but let's do it in a bit more detail. So what you probably have seen is the simplicial category, delta. That's just stuff you find in books about homological algebra. And you can base the theory of simplicial complexes. You can formulate it by just looking at the simplicial category and then study functors from that category. So this category is just the objects are finitely ordered sets. Finite ordered sets, and usually we just take numbers from 0 to n. Representing them, and then the morphisms in the simplicial category. Morphisms would be non-decreasing maps. We are actually interested in something simpler, namely delta S, which is often called the semi-simplicial category. And these are the same objects. But only strictly increasing maps. Yep, and now we see what is there. Of course, endomorphisms are just identity, and if you go from n minus 1 to n, then you just have the choice which point you want to omit if it's increasing. So you get these phase maps or co-phase maps, as Klaus call it, depends on the book you open, which is just omitting the point I. Yeah? Omitting I. So in other words, k goes to k if k is less than I, and k goes to k plus 1 if k is greater or equal I. Yeah? So this is everything you can do. I runs from 0 to n. Okay, and then if you and it's immediately clear that all the morphisms are just products of these, yeah? and the relations you get for these maps are exactly these cosimplicial identities, which is delta j, delta I is delta I, delta j minus 1 if I is less than j. This is what is called the cosimplicial identities, and as Klaus argues, it's an additional relation compared to the Thomson group. Yeah? So that's an interesting interesting similarity. But I will just concentrate on this. Yeah, and now in topology, you know, if you want to study some triangulations and stuff like that into simplices, then topologists are usually interested in contravariant functors, but we do covariant functors, so which is actually easier because we just keep the relations which we have. Yeah. So we take some category C, and then a functor delta S to C is what is called a semi-cosimplicial set. Huh? Or not necessarily a set. We have an arbitrary category, so it's a semi-cosimplicial object. So often denoted by SCO. Yeah. So actually, what does this mean? It just means that you have a family of objects in C, which corresponds to the functor applied to these n's. So concrete, we have some family of objects. Let's call them Fn. And 0, just the images of these n's here. And then you have morphisms between them which satisfy these relations. So this is the functor applied to delta I. I just write it as delta I for simplicity. Yeah? So now delta I are now morphisms from n minus 1 to Fn, satisfying this, the cosimplicial identities. That's concretely what such an SCO SCO is. Yeah. So that's really things you can find in books on homological algebra. But now the interesting observation is, and this seems to be new, at least I haven't seen it anywhere else, is how to produce such a thing from the action of a braid group. So SCOs produced from braids. So that's our first line here. So let's say En, usual braid group generated by Artin generators sigma 1 to sigma n minus 1. And we can take them all together and call it B infinity. That's the inductive limit of the Bn's. And actually, we only need the monoid, sometimes denoted by a plus here. So the monoid generated by that. We never have any need of using the inverses of these Artin generators. So what's my convention in drawing it? It's slightly unconventional because we want to fit it better with the noncommutative probability conventions. So sigma k for me is this. So this is position k, and this is position k minus 1. Yeah. So our strands are actually start with 0. Yeah. So that's the sigma k, and I say I never use sigma k to the minus 1. So actually it's enough to draw it like that, and it's implicit that top right to left bottom is the one which is above the other, eh? Because the inverses never appear here. Okay, so what's the theorem? The theorem is the following. Here, let's look at some action of this thing. Let B infinity plus act on some set, just some set. Act on a set X. Now, so what I want to produce is a semi-cosimplicial set here. So I have to tell you what are the xn's, this family of sets. So xn I define to be, these are just the elements in X with the property that they are fixed by all the sigmas from a certain point on. Namely, we have sigma k x is x if k greater equal n plus 2. So that's my notation for the action of braids on this set. Yeah? So this gives you a family of subsets, and in fact they are included in each other. This becomes less and less restrictive if you increase n. So, and then I have to tell you what my delta i's are, these cophase maps. So the delta I from xn minus 1 to xn, I define them to be x, and I apply I plus 1 up to n plus 1 applied to x. Or more explicitly, that's just a formula which works for everything. Explicitly, the delta n, look at it, that's just sigma n plus 1 applied to x, but x is a fixed point for that because it's in x n minus 1. So delta n is nothing but the inclusion map. And delta n minus 1 is just, so you can omit this sigma n plus 1, it's just there to include that case. That's just sigma n delta up n minus 2 is just sigma n minus 1 sigma n, and going down to delta 0, which is the product of all the sigmas from 1 to n. So, and the theorem is that this is an SCO, yeah? So xn together with this delta I is a semi-cosimplicial object, yeah? So so whenever I think that's a significant result. Whenever you have some action of braids, you get this homological algebra stuff. Eh? So I thought I proved that because you can prove it by writing down a lot of algebra, but you can also prove it by a picture. And I think I can convince you that this should work. Namely, so let's. So what are these maps? These are products of these sigma n. So it's essentially you have some strand going to the right and the different numbers of crossings. Yeah? This is the type of thing you get here. So let's try to prove star. That's what we need. Yeah? We need to prove star for delta i's defined like that. Yeah? So and yeah, say this is, here we have I, j. Say this is n and n plus 1. Here I want to draw my braids. J, n, n plus 1. So let's, and the strands which start here, I want to connect to n plus 1 here, yeah? So the easiest way to do it for I and for j is first to go here to n plus 1 from j. nothing here, doing nothing here in the meantime, and then when we are here, we go to n plus 1 for this strand which starts in I. So then we go down here, and here we need a crossing. Now I've interchanged I and j, so I interchange again. And that's what I want to do with these two strands here. And the other strands are just above and just parallel to each other. Yeah? We go somehow like that. Oh, sorry, one goes here. Just above. Yeah? So what is that? That's exactly what that's almost what we need. Here we have a product of sigmas. Take another one. That's sigma j plus 1 up to sigma n plus 1 here, and then come sigma I plus 1 up to sigma n plus 1. And then one additional crossing, yeah? Sigma n plus 1. So that's the braid we have here, yeah? Of course, that's the same if we move that somehow behind everything else to the left, yeah? So again, I, j, n plus 1. I, j, n plus 1. And now let's try to connect the I first. From here to n plus 1. And now the j wants to go down, but of course it doesn't really work. You have to apply some crossing here. And then you can go to n plus 1. Okay, here you go down, and then you cross here to n and to n plus 1. And you see it's the same kind of entanglement for the ij string as before, yeah? And everything else is above it, yeah? So. Okay, so this is the same. We have just behind everything else, we have moved that crossing a bit. But this one here is, what is it? It's sigma. It's the sigma I plus 1 to sigma n plus 1. Now, here comes the point. This starts one earlier, yeah? So that actually starts with sigma j to sigma n plus 1, yeah? So these braids are the same. So that's almost what we want. And if we apply it to the space here, apply it to x in xn minus 1, then actually sigma n plus 1 applied to x is x. And then you actually get it, eh? Then we just get here delta j, delta I, delta j minus 1, yeah? So that's essentially the proof of that, yeah? So whenever you have such a braid action, you get these identities just by looking at these specific elements here. Okay, so that's completely general. let's now go to some categories which bear some interest for operator algebras. Let's go to category of noncommutative probability spaces and apply that stuff. Yeah? But in a way, that's the basic observation which gets everything going. So I think it's worth to have that picture in mind. So let's now look at the category of noncommutative probability spaces. Yeah, for different authors that means different things. Most general is somehow an algebra and a linear functional. Or a bit closer to actual probability if we take a star algebra and a state. Yeah? Positive, normalized, functional. So a lot of the theories can be developed in parallel. So most often I won't tell you what I'm talking about. Only when it matters, I tell you if we are here or here. Yeah? So yeah, so this should be the objects, and then the morphisms should be the corresponding algebra or star algebra homomorphisms which preserve these states. Yeah? So say some alpha from A1, phi 1, A2, phi 2 is a algebra homomorphism or star algebra homomorphism with phi 2 of the alpha as phi 1. So that would be a morphism. Okay. Yeah, so let's suppose now that we have an SCO. Semi-cosimplicial object, for example, one which we get from a braid action. Yeah? Of course, you see if the braid is not acting on a set, but by morphisms on this category, then you get the SCI in this. You get the semi-cosimplicial object in that category. So suppose we have an SCO, for example, from a braid representation. So what can we do now? Well, so first of all, what does it mean? We have so we have a family of algebras with functionals and we have these delta i's, right? Algebra morphisms now, preserving states. So a n minus 1 phi n minus 1 to a n phi n. So let's interpret. You see here here the delta n's are just inclusion map. Let's just interpret these delta n's from n minus 1 to n as inclusions. Eh? Let's interpret delta n n minus 1, I omit the states as orders right down, yeah? So n minus 1, phi n minus 1, and phi n as inclusions. Well, I assume it's somehow injective, so some technicalities I'm putting under the carpet here, but essentially you can do that, and then your family of algebras becomes a tower, yeah? With these inclusions, and so on, and you get some limit object n, which are just no specific name. Here's some space. So I can produce a tower from that, and yeah, note that fits together very well because by these cosimplicial identities, if we apply them in the special case for delta n, we have delta I, delta n plus 1, delta I, for n is the bigger one. So that means if you do the embedding, and then delta I, the same as delta I, and then doing the embedding on the higher stage. So that means exactly it's compatible. The delta I is the same. Is consistent with this notion of embedding. So delta I is actually a morphism on the whole thing. Yeah. So yeah, we can define what we usually call alpha I, which is just delta I on all an, yeah? Oh, yeah. So you see I switched to lower index because for algebras it's just too unusual to write upper index. Okay, so and this shows that is consistent, yeah? So we get some morphism of this, let's call it A infinity, yeah? On A infinity. Well, actually, if I say on all In, I should say, I should define delta I equal to delta n if I is bigger than n, yeah? So just interpret all superscripts which are too big as embeddings, yeah? That should work. So we get a nice morphism on this tower. And what are its properties? It preserves the state on I infinity. Well, of course, also the states are consistent. By assumption, our morphisms preserve everything. So it preserves this state phi, which is the limit of the phi n's on A infinity. And it has another very remarkable property which makes it really useful. Yeah, I also want to compute it in a simple case. Let's look at some element x0 in A0 and define a sequence xn by taking the nth power of alpha 0, smallest one, applied to x 0. Yeah, so by this definition, the alpha 0 just becomes a right shift on the xi's. Huh? So, question, what happens, what do the alpha, if I apply the alpha i's to such an xn? What is that? That's somehow the key observation here. What happens? So what is it? It's alpha I, alpha 0 to the power of n, applied to x 0. And there are two cases. Namely, the case is that n is less than I. Yeah, if n is less than I, and if n is greater or equal to I. Let's do the latter case first. If n is greater than I, then what happens here? Alpha I, alpha 0 is alpha 0, alpha I minus 1. That's again these cosimplicial identities which are inherited for the alphas from the deltas. So you see, you can interchange that, and this becomes smaller and smaller at every point. So if n is big enough, you just get an additional alpha 0. So you get xn plus 1 here in that case. But suppose n is less than I, then this I is lowered, but it's not lowered to 0. You get some alpha 1 or alpha 2 applied to x 0. But this is just embedding. That's nothing. Yeah? So in this case, this just vanishes. In this case, it's xn. Yeah? So and for this reason, that's just the most elementary computation you can do there. We call these things partial shifts. So they shift from a certain point on, and up to this point, they leave everything where it is. So, why is this so interesting? Well, if you it implies a remarkable distributional symmetry, namely what I call spreadability. A remarkable distributional symmetry, namely this xn is spreadable. So what does this mean? So it's I look at the law of this sequence, the distribution. So any monomial xj1 to xjk, this can repeat, these indices can repeat, so you can also have powers, and then that's a moment, and all the moments give you a distribution, and the distributional symmetry is some operation you can do on these variables which do not change the distribution, and I claim spreadable. So if I apply an increasing function I and 0 to 0, strictly increasing, then it doesn't change that. Yeah? So we have x I j1 dot 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 x I jk. And why is this true? Let's just do an example, and you see why it's true. For example, if you have so y is phi of x1, x3. Now let's take x1, x2, x1, x2, x1. Why is this the same as if you spread it? And I wanted to spread it here to x3, x10, x3. So somehow the order of the indices is preserved, but I do spread it. And the conclusion is that this is that this moment is the same. The vice is the case because x3, x10, x3 is nothing. Let's see, that's alpha 2 to the power of 6, alpha 1 to the power of 2, applied to x1, x2, x1. Yeah? So the alpha 2 only shifts the x2 6 steps, and then the alpha 1 shifts everything. Yeah? So you see arbitrary situation like that you can get from that, and these alphas are state preserving. That's somehow our assumption. Yeah. So you get that. Right. So these distributional symmetries are important, an important topic in classical probability, and in recent years also more and more in noncommutative probability. So you can derive interesting stuff from it. Maybe the most well-known distributional symmetry is exchangeability. Distribution is unchanged for any permutations of the variables. That's a stronger one. And spreadable. So the classical, the most important theorem about exchangeable sequences and why they are important, the classical Finetti says exchangeable leads to a distribution which is conditionally independent. So you get from these symmetries, you get independence properties. You get factorization properties for your states, and in the noncommutative setting, noncommutative Finetti, there are a number of attempts to do that. In our situation, we need the Finetti theorem, which has been proved by Koestler. That's now a W star setting, yeah? So we take W star algebras. So only at this point we really need to go to analysis. Up to this point it's really algebra. So we have W star algebras, faithful normal states. And so essentially, roughly, it says that if you have a sequence which is star spreadable, here we need the star to have some real probability theory, then conditional expectation to tail algebra factorizes. Conditional expectation to tail algebra factorizes. So that means, say E of xy is E of x times E of y, if somehow x is generated by xi's and y generated by xj's and I in I, j in j, and I and j disjoint. So I don't write down what the tail algebra is because I only want to have a quick look at the situation where the SCO and the spreadability really comes from the braid situation. And in this case, we have a characterization of what this tail algebra is. We also know if xn is produced as shown above from a braid representation from an action of B infinity by star automorphisms. Then the tail algebra we use here is just the fixed point algebra of this action. So let's have a quick look what example if we apply this to subfactors. Here. And compare it to the stuff we know from braid group representations there. So example, subfactor n in M to one situation. So I just give you the most basic situation. We have the basic construction M1 and so on. Mi, that's my numbering, is Mi minus 1 together with Ei. And then we have the braid group representation here. So the Ei are the temporally projections, and then the Gi are Qei. Yeah, I want to have finite index. Infinity and beta 2 plus q to the minus 1. Then we have this thing then corresponds to the Artin generator, yeah? Satisfies the relation of the braid group, one of the basic observations by Jones long ago. So, and of course, we can now look, if you want to have star automorphisms, we can look at the adjoint representation. Gives you a representation of B infinity by automorphisms, on the limit object somehow on M infinity. Yeah? So here's a critical point. Star automorphisms exactly if this thing is unitary, and this is only for small index. Eh? So this is an interesting point. So the Finetti in this form only applies if we have a small index. So let's assume that, and let's see what our theorem, our results give in that case. So what did we do? We take some element in M0, and xn is alpha 0 to the power of n x0. That's our sequence, which is now spreadable or star spreadable. Star spreadable would just mean you have to allow stars in this formula, and so the proof only works if you have star homomorphisms. So it works here only for this break representation. It only works for small index. So what's that? You can work that out. So that's at of x0, and this is just alpha 0. So this is product of these deltas. In the first step, it's sigma 1. In the next step, it's sigma 1, sigma 2, or I should write G, G1, G1, G2, G1, G2, G3, and so on. These are these deltas. Actually, you can simplify that at Gn to G1 by braid relations. So what we get from our theory is that such a sequence is spreadable or star spreadable in the small index case. And what's the fixed point algebra here? Well, it's the commutant of all the G's. So it's G1, G2, and so on, prime. And actually, for a small index, that's exactly n. That's old result, which is called the Scow lemma. And in fact, you can use the Scow lemma to see that for small index, actually the powers which we have here from the basic construction, which I did like that, are actually exactly the fixed point sets which we have in our theorem. Yeah? Here, these sets here. Yeah? Fixed point sets for certain sigmas. Yeah? So it's all consistent. In that case, that's exactly the tower we have in our theorem, and we have that xn is spreadable or star spreadable, depending on the index. So let's just write down one formula. So you see what this typically produces. For example, you can do then in the case you can apply the Finetti, so that small index En, you take some x0 and an x1, which is just G1 x G1 star, that's one shifted. Then we get from the Finetti that this factorizes. What's that? That's exactly a commuting square. Yes, that says exactly n in M. Here we have G1 M G1 star, everything contained in M1 is a commuting square. So that's a result you can also find in Goodman-Diller-Harp. Compare Goodman-Diller-Harp-Jones with a different proof. Yeah? So that stuff you can get. Yeah? So, and I want to make the point that that this is really a systematic way to get such factorization properties whenever you have a group action, action of the braid group. Yeah? So refactorizations from braid wraps. And of course the subfactors are just an example here. Yeah? Whenever you have a unitary braid group representations, you can do these things. Yeah, that was just an example. Maybe as a last remark, let me just say we have completely forgotten now that this homological algebra, which we did probability, but there are now also some surprising connections to homological algebra and topology. So other things to investigate. I don't have much to say about that, but it's enough for 2 minutes. If you have an SCO, there is a cohomology theory. Well, the category should be reasonably good. So you have a differential map. You have cohomology. So you can, that's stuff like that. So so it's the most basic form of cohomology, just alternating sums of the deltas. So you need a category where you can multiply with -1 and add things. So you have some cohomology for braid representations. I haven't seen that before, and we, yeah, if you use the braid construction to get SCOs, we get this cohomology. We have no idea what it means. So it should represent some properties of actions of braids. So we computed some easy examples where it's trivial, but I don't see that it must be trivial. So that's really a challenge to find out what properties of braid representations is encoded in this kind of cohomology. And in particular, it applies to subfactors. So it's a kind of cohomology you have for subfactors. So yesterday in the talk about cohomology of subfactors, I naturally wondered if there's any connection of this cohomology in the subfactor case to the cohomologies which were introduced there. Yeah? So I just don't know. Yeah? So that's the very basic cohomology which just comes whenever you have action of the braid group. Okay.
Is there a copy of the cyclic category as well?
Yeah, we don't know. So one of the questions we can investigate now, of course, if we have a representation of the semi-Cosimplicial category, in which situations can be extended to categories with more morphisms. That's a program that's something we want to do. At the moment, we don't know. Yeah.
So we even don't need the degeneracy maps, and of course, when a cyclic operation, if one all includes that, So it would be interesting to see whether such an object is of interest.
If they can be realized by conditional expectations or something like that, yeah? The general is, yeah? That's a good question. But we don't know, I think, at the moment.
Maybe we should leave all other questions in